So my name is Kaushik. I'm a postdoctoral researcher at Argonne Leadership Computing Facility. Today I will be talking about data parallel deep learning. This will be my outline, motivation on why do we need distributed deep learning, some of the distribution schemes, and if you can give me your serial code in 7 lines of code, we can make it distributed data parallel. And so how many of you have already used Huihuo? Okay, so for the remaining people, it will be like really a beginner's hands-on. And for the experts, we will tell you about some of the tips on how to improve it better and how to handle I/O and profilers and other things. And we have some examples on some of the science use cases that we have in Argonne, and finally we'll have our hands-on exercise. So one last time before you all go, the amount of compute used is doubling every 3.5 months according to OpenAI, similar to the Moore's law, and it started with the AlexNet in 2012. Back then people are using their laptops, and GoogleNet in 2014-15 moved from single to a couple of GPUs, and in 2018 that was AlphaGo, and neural architectural search that has an enormous compute because it has to search for the best architecture, and you can see that with ResNet 50 what it takes 14 days with NVIDIA M40. It should ideally take 1 second on Summit if it scales ideally. This includes the bandwidth, loading time, and all the other network related issues. This is another interesting motivation. This is from GPT-3. I see cool images from GPT-3 posted in Slack, and you can see that it took 3,640 days to train GPT-3, and that is almost 10 years, but OpenAI was launched only in 2020. So if you are doing that on a single GPU, that's like 355 years, and they used 1024 A100 GPUs, and they were able to do it in around 34 days. So these numbers are just, I took it from Reddit and Google. I don't have the references. So the cost estimated is around $5 million just to train the GPT-3. So what does this all mean for you? If you are able to train your model on using scale with Huihuo, you will be able to test a lot of hypotheses in a very short amount of time. That can also get you published a lot and graduate faster. So the need for distributed parallel training on HPC. So we see that the model complexity is increasing, and there's a dramatic increase in computation. So previously people used to train with megabytes of data. Now we have like terabytes and petabytes of data used for machine learning. And the increase in computational power will be mostly coming from parallel computing. And I see a lot of domain scientists will be coupling their HPC simulations with machine learning in the future. And so there are 2 parallelization schemes for distributed learning. One is model parallelism, the other one is data parallelism. In model parallelism, we just have 1 copy of the model, and we can have 4 different workers share a part of the model. Here you can see that the result for worker 4 is dependent on the worker 3, so there will be a lot of local communications. This looks conceptually easy, but practically this is a little hard, and today we will be focusing on data parallelism. Here we have the copy of the model in different workers, and we will take a subset of the data and train it on different workers. So here the problem is there will be a lot of all-to-all communications and synchronization between them, and recently there is a combination of both model parallelism and data parallelism. For example, if the model cannot fit into a GPU, then they have to like share both the models and the data across many different nodes. So for today's hands-on, we'll be using Polaris. So I think Kyle got like 200 nodes for everybody to use. So that's like 200 times 4 GPUs. You have like 800 GPUs to use, and this Polaris was, I think, made public 2 days back. So it will be the early users to use, and it's ranked 14 in top 500. And yeah, so I'm going to talk about this 7 steps that can take your machine learning code and scale it on thousands of GPUs. The first one is should be very easy. Just initialize your hover, like import hover and hover in it. It's similar to MPI. And second step is pin your GPUs to each process. Like when you say run it on 100 processes, that means you need 100 GPUs to run your machine learning code. So that's second step. And we don't want all the process to do the checkpointing or printing the total time, so we just ask rank 0 to do it. And I'll talk about the other four steps: scaling the learning rate, distributing the optimizer and broadcasting model, and things like that. So just to convince you, this is very easy. First line of code, import hoverword and hoverword.init. And the second step is you pin your local ranks to GPUs, so that when you ask for like 100 process, it runs on 100 GPUs. 2 lines. And the third one is optional, but when I see a lot of people are running on very huge HPC models, and you need to do checkpointing. So you would ask just the rank 0 to do the checkpointing. So this line should be already in your code. You just add this part. Only if I'm rank 0, then you do the checkpointing. And finally, printing the total training time is just rank 0. So that's first 3 lines to be for you. And as we saw in the morning talk, so the entire machine learning is, it boils down to minimizing loss function. So you have your inputs, you have your weights. We change our weights at every iteration, and we are trying to find we are minimizing the total loss. So we use stochastic gradient descent, and we take a batch by batch of data, and we train it across our network. So yeah. So the fourth step, when we are not parallelizing it, so we'll have a small batch. So the steps would be like smaller and smaller, narrowing down to the lowest point. Now we are using a large batch, and there are a lot of workers which are working on that. So we have to, when the mini batch size is multiplied by k, we have to multiply the learning rate by k. So this you may have your own set of optimizers, and all you need to do is add this part to your learning rate. So this is step 4, and step 5 is in data parallel. You take sub batches of your data, give it to different workers. You calculate your weights and gradients, and once you calculate, you need to share it with the other workers so that they can calculate their average gradients. And once you get your average gradients, you train the model again. So this sharing is done through MPI all reduce. So basically, the first step is like you have to distribute your model and distribute your optimizer. So this is their 5th line of code. And so yeah, so training the large batch. So now we have 2 options. Suppose you have 256 data set, you have 2 workers. You can give 128 to one worker and 128 to another worker. So that would be your strong scaling. Yeah. So the other option is to give the entire 256 data set to the first worker, and again another copy of entire 256 data set to the second worker. So that would be your weak scaling, and it has been observed that having a smaller batch does not scale well, because there will be more communications into it, and reduces the per node throughput, and having a global mini batch reduces the number of updates. So it's preferred to have a large mini batch, and there have been numerous studies on this. However, having a large batch has two challenges. The first one is convergence issue. So if you use a large batch at the initial stages of the training, the model is far from the optimal solutions, and the training is not stable. And the second problem is generalization gap, which is the model may have better accuracy on training, but when you do your testing, then it would have a lower accuracy. So the study shows that having a smaller batch has a similar accuracy in training, smaller batch and larger batch, but when it comes to testing, there is a degradation in the accuracy. So that is because it generally gets trapped into the sharp minima. As you take larger and larger data, it may never enter the sharp minima, and the black line is a training function and the red dot is a testing one. So there will be a difference there. So yeah, and so in order to solve that problem, we have a warm-up stage. So what we do is we gradually increase the learning rate. You can see that when there is no warm-up, there is a difference in the error, and when you have a gradual warm-up, it stays stable. And even this solution works only when you have the batch size till 8K, and this does not help if you have a larger batch size, and this is an area for the research. And yeah, so people have come up with what is the maximum batch size that I can use for a model. So that was an interesting question. If I have 2,000 nodes, why can't I use the entire 2,000 nodes on Summit or Frontier? My model has a peak at 700 nodes or 800 nodes. That's because it is limited by the batch size. The number of workers should be lesser than the maximum batch size. So hence you cannot use all the nodes for your distributed deep learning. And yeah, so the sixth step, as I said, you have to broadcast your variables, and you have to take the average of the gradients, and you have to warm up the learning rate and pack your callback and give it to your network. And the last step is just this part, which is, so you have now three ways of having your input file, which is you can have one image per file, or a batch of images per file, or you can have your entire set of images per file. The problem of having one images per file is like there will be a lot of files that it has to go through, and there will be a huge metadata overhead in opening and closing files. So it's preferred to have a batch of images per file, and you just have to add this part. And so this is an example with TensorFlow. Yeah, the same things. Import your TensorFlow, call the init, share it with the rank, and pin it to your GPUs, add a distributed optimizer, and only if it is rank 0, print your checkpoints. And it's the same case with PyTorch and Keras. And so these are some of the results from AlexNet, ResNet, and Inception. You see the white is an ideal scaling, and the blue is what we achieved through Horvath when you're scaling from one kernel node to 2024. So this gap is the communication waiting time. So you can see a similar trend on all the different models. And here you can see that with AlexNet, when you go from one node to the two node, the compute time is does not increase, but there is a huge communication time that's happening across all the different models. So this is a good place to have an overlap of communication and compute to minimize the training time. So this indicates there's a large overlap between compute and communication here. So for today's hands-on, you can use a number of profilers. 2 days back we learned a lot about profilers. So all you need to do is include your LD preload path when you run your when you submit your job, and you'll be able to get the profiler results. And you can see that so the most of the time is spent on MPI gather. Remember this is from all reduce when the gradient is being shared to other nodes. So clearly there's a load imbalance here. So this MPI flat profile is to see what is happening, and when you want to see when it's happening, so you can use the hover timeline. So yeah, so all you need to do is have this environment variable, and you will get a JSON file, and you can use your browser and load the JSON file, and you will be able to see the profiler results. And it's like a spectrogram, like what is last 2 days back. You can always zoom into it and out of it and see. So this is the result for CPU, and this is the result for GPU, and you can see that the all reduce in GPU is just 19, and here it's 133. That's because of the NCCL all reduce library from NVIDIA optimizes some of the all reduce there. So we also have our in-house profiler for deep learning. It's called DLIO or VaniDL. That uses Darshan in the backend, and it is primarily for looking into deep learning workloads and the IO bottlenecks and data management in machine learning. You can try that one too. And yeah, so till now we were seeing how to parallelize this part, and as with every other HPC applications, so this part is almost serial, and we also need to parallelize this part. So some of the tips here is we should use the parallel IO concepts like MPI IO, or use parallel HDF5, or pre-process the raw data, change it into binary formats. As I said before, avoid file per samples, and you can do some prefetching the data before starting this. So, and these are some of the science use cases from our colleagues from Argonne. This is a cosmology project. I'm not a cosmology expert, but I think they are classifying the galaxies into spirals and ellipticals, and you can see a linear speed up of to 64 GPUs. So 5 hours of using 1 K80 GPU to 8 minutes of using 64 K80 GPUs. And the second use case is brain mapping. It's a segmentation work, mapping brain cells from the electron microscope data. This is the throughput and training efficiency, and when you increase the number of nodes, you can see scaling results from here. And yeah, and so yeah, the summary is there's an increase in model complexity, and the amount of data is growing. Data parallelism can scale efficiently in HPC computers, and you should use the warm-up steps to stabilize the initial stages. And distributed learning requires efficient and scalable IO data management. And yeah, so that's it from my talk. Today we will be trying out some examples. We have everything set up ready here. All you need to do is just copy the examples from here. Before going to this, I would like to hear some questions and thoughts.
Is your in-house profiling file available for us to use also, or just in-house?
Sorry.
Do you have some in-house profiling tool for machine learning workflows?
Yeah, so the VanIdeal, I think Huihuo, you can talk more about.
It's more for I/O part. The provider we use the Dacian to get out the I/O access pattern, and then we have the processing tool, the Python processing tool for VanIdeal to analyze the Dacian log.
Okay,
Yeah.
that's kind of thing we really want to have access on, because we have seen a lot of problems with
Yeah,
I/O.
I think our code is it's on the GitHub repo public.
Okay.
So we also have the installation on DataGPU. Yeah, if you are interested to use it, you can talk to us.
Yeah, I'm trying to use it on AlphaFold, and that would be very useful. Thank you very much.
We'll be interested to work with you.
Okay, thanks.
Oh, yes.
Do you have any metrics for how this speeds up compared to the torch distributed data parallel? Or even TensorFlow's built-in mirror?
I have some examples here in the training files. Here you have the TensorFlow versus PyTorch versus Keras, and we haven't tried it, but they can always test it out. Yeah.
What we learned is that TensorFlow, Horovod work well with TensorFlow. If you use PyTorch, DDP, distributed, that's kind of have higher scaling efficiency compared to Horovod because of implementation. The support for PyTorch the Horovod support for PyTorch is not as good as the support to TensorFlow. It's more because of, I think Kaushik mentioned the overlap of the computation with communication part, right? So the support for that in PyTorch is not as good as the support for TensorFlow. So if you use PyTorch, I would suggest use DDP.
And that will be faster than TensorFlow with Horovod, or slower?
That probably, if you...
I would say it'd be faster because the Horovod, which objects it can actually communicate is at a higher level than like PyTorch. DDP is built like straight into PyTorch. You can execute incomplete gradient updates and be communicated as soon as they're done. Whereas I believe Horovod has to wait.
But I think his question is asking that if you have example running with TensorFlow plus Horovod compared with PyTorch plus DDP.
Yeah, DDP would be faster, I would say.
DDP will be faster.
But yeah, it'd be interesting to.
Yeah, I think in some cases it will be faster, but of course we don't have like very broad spectrum of the survey for that. But for sure, if you use PyTorch, then use DDP instead of Horovod. Yeah, and the change of the code is pretty similar.
Yeah, I have one question.
Yeah.
So what is the correlation between the batch size and the accuracy? Because I see there's a table that you showed about the LM, and there was a difference because as per my understanding, no matter what batch size you're using, every epoch has to touch all the data set, right? Every epoch. So why there's a difference between the small batch and the large batch size, the accuracy?
Yeah, so maybe I can try this one. So when you have small batch, when you're traversing down the optimizer, you will slowly, gradually increment step by step towards the lowest point. And when you're using a very large batch, it will be faster, like it will come down very fast.
Maybe I can add. So the key thing, you can look at the paper that put in the slides if you go back to the previous. But the hand waving, I think it's also because it's using the stochastic gradient descent. So if you use large batch size, then the noise, the statistical noise, is smaller. When the noise is smaller, it tends to be trapped at the sharp minima. But if you have a lot of noise, it's quickly jump over the sharp minima, and then it tends to stay in the flat minima. So smaller batch size will have large noise. You can think about that, and so that's why smaller batch size
it's have higher possibility to go to the flat minima. And the flat minima has a, it's minima both for the training and then for the testing, right? But if for the sharp minima, it may be good for training, but then for testing, because the increase is so sharp, it becomes not as good, not the minimum for the testing.
How exactly let me, what is exact definition of a small batch and large batch?
Okay, so that's the next, go further down.
Oops, I don't have it.
There is a plot that's showing that different models have the different maximum batch size. Go down. Yeah, here. So it's actually really depends on the model that you're using and even the data set. So for different model, maybe for example, ResNet model, it shows that 8,000, the batch size 8,000 is the good batch size, right? Going beyond that is too big. But maybe for other model, like MNIST, right? MNIST, this is a 1,000 batch size. This is the total batch size, right? Then going beyond that, it's considered to be big, So it's different model. So it's good practices that you just keep scaling, and then train your model, see whether you lost your accuracy or not. If you lost your accuracy, then reduce the batch size a little bit.
And this is also very important, where the number of workers is tied to the batch size. So just because you have like 8,000 GPUs, you cannot use all your 8,000 GPUs.
Yeah, that basically limits the number of GPUs you can use.
Let's take an example of ResNet 50, and I have like 1 terabyte of data set. Because ResNet 50, you can use some standard like the byte size, and I'm trying to run or scale that on 1,000 of Summit compute nodes, right? Every Summit node compute node has 6 GPUs in it. And what byte size is like optimal for my use at that time?
So for ResNet 50, I think the study shows that the maximum global batch size is 8K, right? 8,000. So if you want to use like 6,000 GPU, then the local batch size will be just 1 or 2, right? But that will degrade the computational performance, because you just use one batch to fit into the GPU, right? So it's a kind of balance. So I would rather use like smaller number of GPU, but the batch size per GPU is larger to make the GPU busy, right? But still keep the total global batch size smaller than 8,000.
Yeah, and in your case, then it would be like just one operation GPU and waiting for the communication the entire time.
The x-axis of that plot, the number of workers.
I think it's batch size.
Batch size.
What's the y-axis in?
2. I think
Oh,
number
actually-
of nodes and number.
Actually, maybe the x-axis is the model size. The model size. Y-axis is batch size.
Yeah, you can always check this.
Yeah, we should take a full screenshot of that.
Yeah. And so, yeah, so you have 4 sets of training examples here that you can try it out on Theta Polaris, and on side by side, you can compare what's the added code for scaling it with Huihuo. So, yeah, the things.
So your module low data size is not working on Polaris.
Oh, so if you see the Polaris code, you don't have to use module data science. I think Kyle will be able to answer that.
That's probably good. You can use the data science one. That's the Polaris one for sure.
Okay. So
I
yeah,
also can't load data science on Theta GPU.
I probably got rid of that one. Is that normal? Use just the latest Conda
Gotcha.
module on either machines.
So yeah, if you run exactly like this, then you will be able to grep for the final training time, and you will be able to plot your scaling plots. So I think here this is a better reference, and here you will be able to see. And the reason why here when you go from 4 GPUs to 8 GPUs, the total training time slightly increases, because this is just a sample example. If you need to perform it better, you need to add more work to compensate this. Yeah, so and I think that's it. You can try the hands-on. So were you all able to submit your jobs to Polaris? Do you have any issues there?
This as well too.
Yeah, not able to get it too, so.
So.
Yeah, it's just right. Is this minus I on Polaris one? Is this right? Because it's not.
Oh, first one. Oh, is hyphen I the interactive?
There's L.
Oh, L. Okay. Yeah, if you don't get your jobs on Polaris, maybe you can jump to Theta GPU. So you first have to log into Theta, and then SS to Theta GPU SN1 for running on Theta GPU. You can also, I think the code has for threading. Yeah, so if it's on CPU, you can always use the threading.
The Polaris submission script, you might need to add a change directory CD to where the, yeah, so this script buried in the submission subfolder on the GitHub.
Okay.
And I think you might have to CD to the directory with the Python script.
So yeah, your working directory.
Put that in the submission screen.
My cursor is changed here. I can't copy or do anything from this.
I can make a change.
Yeah. everybody's waiting on the queue then. Kyle,
20, depends on the day, how many hardware failures there are. It's like 32 nodes of data GPU.
so yeah, you can see the
The script that you had last,
six,
you get 16.
yeah.
And if there's only 20 nodes.
Oh, that one has
No, that's for Polaris, right?
Polaris.
Polaris has
Data
5 nodes.
GPU.
Well, the data GPU script's asking for 16 too. Maybe I'll update that one too.
Yeah. So there's someone with 16 nodes on data GPU.
I'm seeing only one node.
Yeah, I see one node.
One node.
Data KNL is asking for 16.
Yeah. Yeah, but when you do the Q sub submission, make sure you are in the folder where your Python script are. So you can copy the submission script outside of the folder. Then you in Polaris, I don't think, so maybe you can just run up to 2 node or 4 node. No need to run on 16 node because it doesn't scale for that well. For the smaller work, small model.
So Kyle, do we have an activity page for Polaris too? Like
Not yet, no.
Okay.
How can we visualize the results after?
Sorry?
How can we visualize the results?
Visualize the result. For now, for these examples, I think we are just redirected to, so I think by default the name would be like Polaris output, and you can grep for total. And are you looking for like plotting it, and maybe matplotlib and other things would be helpful?
That web page you show,
Sorry?
you show like traces.
I see. Okay. Okay. Yeah.
That's a
Oh, that's yeah. That's a profiler. So all you need to do is in your Q job file, you just need to add a LD preload for the MPI profiler, and for hover timeline, you just have to set this environment variable. And all you'll get is just a JSON file, but you have to open your browser, download the file, and load it here, and then you will be able to zoom into it and see more details on what it's doing.
Yeah, you can download that JSON file to your local machine and then visualize it with Chrome browser. But the previous page, the MPI profiler, that one works only on Theta GPU for now. We will make it also available on the Polaris, but I haven't built that yet. So this will just show the MPI communications involved in the training, you know. And so that, if you go back, once you have this LD preload and run the example on the directory, it will have a bunch of files called MPI trace or MPI, I think it's MPI something, you know. and then you can open it up, and it will show exactly this information.
API profile could be?
Sorry?
The name, default name, yeah. What is the default name for
This,
yeah.
the profiler? Yeah, after this, after put this LD preload and run example, there will be a bunch of text file.
Yeah, I have it.
Oh, you have it, and then you can open that. Is it called MPI underscore trace, right?
The profile.
Let me just go and check. Yeah, MPI profile. Then you can open it up, like for example, this profile 188.480.
Run 0.
Yeah, the run 0. That's the run ID.
Okay.
You just use your text. Which one? Text editor. Open it up, and then it will show the MPI profile. You can just emax over time. Then you can type.
Yeah, sure.
No, yeah, that's what I said. So if you want to know what is happening, so you can see, okay, what is this, how many calls and what's the average bytes and what's the total MPI communications, then this will be useful. But if you want to see when, and if you want to dive deep details into those function calls, which particular operation is taking more time. Yeah, some things are similar, but it also has more information on a much better GUI.
If I have one MPI rank failed in training, like due to some error, right? So which one is good? What timeline are the previous one?
One MPI rank is failing.
Let's say one of the MPI in the training failed, right?
Okay.
So which one is more useful? Which one are the previous one?
Let me think.
So yeah, that's okay. Yeah. Thank you.
There's also another so his question is, if one of his MPI rank fails, which profiler is useful for me?
One of the MPI
Yeah, let's say like my training failed due to one or two MPI ranks, right?
Yeah.
Some error, whatever, like some segmentation fault or whatever that was. So this whole timeline trace file is good, or like the previous one, the perf tool MPI.
Well, they give you two different information, right? So this timeline show you when those MPI communication happens, right? But the previous one, it shows you statistics about the total MPI communication time. For example, here, total communication time, and then show us the breaking down about the different MPI or reduced code, like with different message size. So it's more about a statistic information, right? It didn't tell us the timeline, when those MPI communication happen, right? But versus this Horova, you can see clearly in the timeline base, right?
Like you mentioned, like MPI, this one. Is it something like internal to Argonne or is it
This is a tool actually developed by people called IBM, Bob. So it's open to the public. It's called HPC-TW, and sometimes called MPI trace. It can do more things than just providing this trace information. It can also do the timeline, but of course you have to set another environment variable to produce the timeline, like showing when the MPI communication happens. By default, it will produce this statistics result. This library is open to the public. You can search HPC-TW or MPI trace. You will find that. So we built that on our machine, so you can just load it.
So what's the name of is it VaniDL or is it DLIO?
So VaniDL is another library we developed for the I/O profiling. So to understand how good the I/O part is, that's the one. And we also have another code called DLIO. Is more kind of trying to create an I/O benchmark to mimic the real workload. That's help us to understand the I/O, the data process data loading part for the deep learning.
Yeah.
Yeah, that's the DLIO benchmark.
Yeah, just pip install.
Yeah, I think if you do those benchmark, like run from 1 GPU all the way to 64 GPU, and then you generate a profiling result, like MPI communication, you will find that how the MPI time increase when go to larger number of nodes.
So, yeah.
Yeah, that's the reason that why the total time doesn't decrease when you go from 4 to 8, because you have 4 GPU in a node. If you want to run in 8 GPU, then you have to go across the node. The node-to-node communication kind of make it slower.
So there's one more question.
I was able to do the timeline part. I downloaded the GPU.json file to my local machine.
Okay.
Then I'm uploading it as a text file like this.
Sorry.
I already have a whole working code.
Okay.
So I did that.
You cannot do. You just load reading that directory, right? So you have to. Could you go back?
Yeah.
Go back to your Chrome browser.
Browser.
And open it and Chrome trace dot trace. I think it's comma.
Let's see.
Let me.
Yeah.
I forgot the address. Yeah, Chrome double slash. So if you want to visualize timeline, you have to go to this. Go to this, and then it will show this the whole interface, and click load the JSON file. Good. Okay.
So it works? Okay. So I was, you had a question?
No, no.
Okay.
No, I'm saying like you guys can use the perfecto UI. There was like
What was the profile?
it's not profile, it's perfecto UI. There's also like the web browser kind of thing. So you just upload your timeline file, like the JSON file, and it will display the same thing.
Okay.
Okay.
With a better
Good.
UI?
Yeah.
Okay.
Good to know.
Yeah. So I think it's time.
Which one? That's Theta GPU and Theta. Yeah. Polaris, we have to build that, and then we'll make it available. I haven't built that yet. And open your browser.